So theorem 5.38, if f is a Grobner basis for IDQ f, and oh, by the way, this is one of the most important, this actually is the theorem that makes everything happen. And this is theorem 5.38, is that if we have a Grobner basis, then for any polynomial p, we have p reduces completely to 0 if and only if p is in that ideal. So this gives us a way to check for if the polynomial is in the ideal. Is that all we need to do? If we are lucky enough to have a Grobner basis, all we need to do is check that this polynomial reduces finally to 0. And one of the great things that Harrison proves is that this process always terminates, which is unlike the solving of the system of linear equations. So, so the proof of this can be found on Harrison 409. So if we can just, so now we've just reduced the problem defining a Grobner basis. So we can find that for some that. So given some set f, if we can find a corresponding Grobner basis for the ideal. So if we can, so essentially, if we can find the Grobner base, if we have a set of polynomials, finite set of polynomials f, replace it with a equivalent Grobner basis, then all we need to do to prove that a polynomial p is in the original ideal QS is just to prove that the polynomial reduces under the corresponding Grobner basis f to 0, and we're done, which is awesome. But here's the great thing: we can always find a Grobner basis for any ideal finited by a finite set of polynomials, and this is by Buchberger's algorithm, and it's under Harrison. And Harrison gives the program on page 410. And moreover, since the reduction system always terminates, we have a decidable procedure to test ideal membership in the ideal generated by the finite set of polynomials f under ring Q. Thus, because IDQ, by the previous theorems, we can determine that the validity of any universal formula in the theory of torsion-free rings or the theory of integral domains of characteristic 0. And the reason why we can't do it for just rings right now is because that equivalence we showed was with the, we have to show ideal membership of IDF in the ring Z, which is not the ring Q. So for the theory of rings, we need to generalize Grobner basis to Z, X, and to do this, the Harrison references Kandri-Rodi and Kapper in the algorithms for computing Grobner basis of polynomial ideals over various Euclidean rings. And it seems that this can be extended to the whole theory of rings. Anyways, thank you very much for listening. If you have any questions, please email me at pvong@stanford.edu, PVUONG, or Skype me. I'm pvong. 87. Thank you very much, and you can also look at pvong@stanford.edu to find it in particular. Thank you very much, and thanks for listening. Bye.